So when we were taking derivatives before, we saw that it was easy to get second derivatives and third derivatives by just continually taking the derivative. Can we do that implicitly? Well, yes, there isn't any reason that we can't keep taking derivatives. So if we want to find the second derivative, say in this case implicitly, we're going to do it like we did before. So this is the function equation we had earlier, and this time we're going to find the second derivative. So let me just go over the finding of the first derivative quickly. We did the derivative of both sides with respect to x, and so that was 2x plus 2y dy dx equals 0. And then so we solve 2y dy dx equals negative 2x and divided over to find that dy dx with the 2's canceling is negative x over y. Okay, so that's fine. Now how do we go and find a second derivative? Well, we have the first derivative, so we just take the derivative of it. All right, so if we take the derivative again of both sides, like this. So what's on the left-hand side? Well, that's really just the second derivative. Okay, now how about on the right-hand side? Well, what we have in here is we have a quotient, minus x over y. Those are two functions of x. So we have to do the quotient rule. So the derivative at the top with respect to x is minus 1 times the bottom as it is, y, minus, from the quotient rule, top minus x, times the derivative of the bottom, so dy dx, because it's just really 1 dy dx, over the bottom squared. Okay, so now what do I do? Well, notice I have this dy dx in there, in addition to x's and y's. But that's okay, because I know what dy dx is. I've already calculated that. So if I go up here now, I could do this. So I have negative y plus x, and then I already found that dy dx is negative x over y, all over y squared. Okay, so now if I want to get out of this multi-tiered fraction here, a nice thing I could do would be to multiply by y over y. Okay, so I get minus y squared when I multiply that there. And when I multiply it here, the y's will cancel, and I'll get minus x squared all over y cubed. Okay, now that looks good. But notice I could actually go a little farther. What if I did minus y squared plus x squared all over y cubed? Doesn't look like it made a big difference, but remember how this problem started. Given that x squared plus y squared is 25. Oh, so this right here is actually 25. So I could actually say minus 25 over y cubed, and that's my second derivative. All right. If I wanted to, I could keep going and keep getting higher derivatives by just keep doing an implicit differentiation and look for places where I could substitute. Now, it won't always happen everywhere, but there'll be places where you can substitute back first derivatives, the function itself, that sort of thing. Now, we're not going to do a lot of second derivatives implicitly, but I wanted to show you that basically it's certainly possible. There's nothing wrong with the idea. All right, so let's do a problem where, again, like I mentioned before, we're just finding tangent lines. Okay, we've done this before. The big thing about differential calculus is finding the equation of tangent lines. So let's do it, even if it's a case where we have to do it by implicit differentiation. All right, find dy dx, the derivative, evaluate it at the given point, and find the tangent line at that point. All right, so here is our equation which involves our function y, and here's our point. So I notice that if I'm going to find dy dx, this is implicitly defined, so I'm going to do implicit differentiation here. So take the derivative, both sides, with respect to x. All right, on the left-hand side, sorry, derivative with respect to x of x to the 2/3. 2/3 x to the 2/3 minus 3/3 is minus 1/3. Plus derivative y to the 2/3. 2/3 y to the minus 1/3 chain dy dx equals 0. Okay, so just solve for dy dx now. So 2/3 y to the minus 1/3 dy dx is minus 2/3 x to the minus 1/3 divided over dy dx. Now the 2/3 are going to cancel, and I'll just get minus x to the minus 1/3 over y to the minus 1/3, which there really is no reason to leave it like that because I have two negative powers. They're basically in the wrong place, so I could just flip up. So minus y to the positive 1/3 over x to the positive 1/3, just to make it easier because I'm going to be plugging in. Okay, so if I want dy dx evaluated at the point 8, 1, that would just be minus, so x is 1, so y is 1, 1 to the 1/3 over x is 8, 8 to the 1/3. In other words, negative 1 to the 1/3 is just 1. 8 to the 1/3 is a cube root of 8, which is 2. And so there we go. There is the derivative evaluated at the point 8, 1, which we also know is the slope of the tangent at 8, 1. So if I want the equation of that tangent line, well, I know the slope is minus 1/2, and I have a point 8, 1. So I'll use point slope. Y minus 1 is negative 1/2 x minus 8. Y minus 1 is negative 1/2 x plus 4, giving me y equals minus 1/2 x plus 5. And there is the tangent line to the curve at the point 8, 1. Okay, so we're still, again, talking about derivatives, derivatives being the slope of the tangent line. So no matter how we get the derivative value, we can use it to create the tangent line there.